So, at the end of our last video, we decided that a plane was a group of infinitely dense lines parallel to each other with one line intersecting all of them, and so that would make them have to rely on a plane. However, we found that that constraint wasn't right because that would mean that all of the parallel lines, while they would not intersect each other, if they were only dealt on one line, they could skew up and down.
They could rotate as if the non-parallel line was an axis.
Right, and still be parallel with each other.
Right. Or
So-
at least non-intersecting, I don't know.
Yes.
Yeah, they would still be parallel.
Okay. So to fix this, we decided to constrain our definition even more by saying instead of having one non-parallel intersecting line, if you have two non-parallel intersecting lines that intersect each other also, then every line that intersects both of those crossing lines would be within a plane.
Yep.
And that would constrain them from skewing. Except for at one point, at the
Yeah.
intersection of our two original lines. And our problem there is that since both of those lines are at the same point, another line could skew and
Could be anywhere in the two
could
pi.
be
Exactly.
anywhere within.
And it would still be parallel to all the other lines and go through both.
Okay.
So now we still have this small hole in our definition.
Right. Okay.
However, we're going to take that small hole and we're going to turn that into the actual
Definition.
mathematical definition. What we're going to do is we're going to make that line perpendicular to the plane. And so by saying that everything in the plane is perpendicular to that one line, we can define the plane.
Right. So we have this skewed line. Instead of just letting it float around wherever it will go,
It's been skewed at 90
Make it
degrees.
90 degrees.
Okay.
Force it
And
to be like that.
So we say that the skewed line is a normal vector. And that normal vector intersects a plane at point P, which was our original intersection that we were
Had the
having
problem.
trouble with. And so now we say that any line that intersects our normal vector at point P and is orthogonal to the normal vector, well, normal, I guess that means orthogonal,
Same
Would
thing,
be-
perpendicular, 90
right.
degrees.
would be within the plane, would lie within the plane we're trying to define.
So basically, intuitively, you have a line and a point on that line, and then to define the plane, if you picked a point and the line between the point that's on the line and the one you picked is perpendicular to the special line, then the point you picked is in the plane.
Excellent.
Mathematically, we say that it's any real number that is this line x minus the point P of intersection dotted into the normal vector equals to 0. And whenever that is the case, then that's the line, meaning that it's perpendicular, that it's in the plane, that it's perpendicular, that it's flat, it's not skewed. It's the plane.
So we're going to use the dot product as the definition of perpendicularity.
Yes.